Okay, we're going to talk about the harmonic series, and it's an important divergence series. Again, there's quite a bit in this lecture, so we're going to break the video into two pieces. I'm going to start with the definition of the harmonic series. For n an element of the natural numbers, define h sub n to be equal to 1 plus 1/2, etc., all the way up to 1 over n. Okay, and we're going to let h be equal to the sum of n equals 1 to infinity of 1 over n. So basically, this h is the limit of the sequence of my hns. Okay, I'm going to start with a lemma. Which will seem totally disconnected from anything we're doing. For n element of the natural numbers, list 2 to the n plus 1, 2 to the n plus 2, 2 to the n, etc., all the way up to 2 to the n plus 1. Okay, that list contains 2 to the n numbers in total. Okay. And this is not difficult, but we'll prove it anyway. Recall that if n plus 1 up to n is a list of consecutive integers, it contains n minus m plus 1 numbers in it. Now simply note that 2 to the n plus 1 minus 2 to the n plus 1 is equal to 2 to the n plus 2 to the n minus 2 to the n plus 1 plus 1. And just do the arithmetic, it's equal to 2 to the n, and so we're done. So we're now ready to show that the harmonic series diverges, and so let's state it in a proposition of 3 parts. First, that hn plus 1 is greater than hn. Second, that h sub 2 to the n is greater than 1 plus n over 2. And third, that the sequence of hn diverges to infinity, and so that will be that the harmonic series diverges. And so to prove 1, we just take the difference between hn plus 1 and hn, and since they're equal up until except for the fact that hn plus 1 has one more term, their difference is that one term. It's 1 over n, and it's greater than 0. Therefore, hn plus 1 is greater than hn. Okay, so that's easy. Okay, so we're going to show that h to sub 2 to the n is greater than 1 plus n over 2. Well, what we do first, we just write out h to the 2n, or excuse me, h sub 2n. It's 1 plus 1/2, etc., all the way out to 1 over 2 to the nth power. Now, what I do now, I trade this in for something that's smaller but easier to deal with. I trade the 1/3 in for a 1/4, and basically anytime I get up to a power of 2, I go to the whole stretch and replace the denominator with the largest denominator, thereby making it all smaller. Okay, that way I can get down to the line 3 and I can group things together. Okay, and so I can group all of my sums of reciprocals of powers of 2 together, and basically 1/2 is 1/2, 1/4 plus 1/4 is 1/2, 1/8 plus 1/8 plus 1/8 plus 1/8 is 1/2. If I do 1/16 8 times, that's 1/2, and so basically I group these all together and I get 1 plus a bunch of 1/2. Well, there turn out to be n of those 1/2, and so I group that together to n over 2, but my h sub 2 to the nth is greater than n over 2. And then finally note that the sequence 1 over 2 to the n is not bounded above, and h over n is bigger than that, and so it's not bounded above. Okay, so now we're going to connect h sub n and the natural log of x. And here I'll illustrate it with a picture, and again, as always, it can be proved rigorously, but let's just look at the picture this time. I have my curve from 1 to n, and it's above these rectangles, which are area of 1/2, 1/3, etc., all the way up to 1 to the n. And so I see that my natural log of n is bigger than h sub n minus 1. Okay, and so now if hey, my natural log of 2 to the n is bigger than h sub 2 to the n minus 1, which is greater than n over 2. And so since n over 2 goes off to infinity, my natural log of x will go off to infinity. Okay, so and we can also show that the natural log of x is not bounded below, because the natural log of 2 to the negative n is equal to the natural log of 1 over 2 to the n, which is equal to negative natural log of 2 to the n, which is less than the negative of n over 2. Negative n over 2 is not bounded below, and so the natural log of x won't be bounded below. Alright, this bit right here isn't connected to natural log or the harmonic series, but I wanted to talk about it anyway. So another way of viewing sequences, you can view a sequence as a function from the natural numbers to the real numbers by taking n to x sub n. Okay, so it's just a function, and so you can think of then the sequence then as an infinity tuple, okay, of real numbers. Okay, so that's one way to do it. And so when you're thinking about it, it's sort of like a vector space, right? But a vector space has operations. Scalar multiplication, well, you can just multiply each of the if you multiply the sequence by a, it's just like multiplying each of the members of the sequence by a, and you can add together two sequences term by term. Okay, and so we can do algebraic operations with sequences and tell you how well they behave, and so that's what we're going to do in the second half of this lecture.